Okay, so upon request, I was going to go over the binomial series one more time. And the one thing that I do want to make clear, though, is that this is not something that you need to know how to generate. You just need to know how to do problems using it. So you really just need to know how to apply it in examples like number 2, or in problems like example 2. Also, by the way, I think I finally found a good set of headphones that's going to work with this, that's not going to catch a lot of the outside noise. So please let me know if there are any issues with this. Okay. So what I'm about to do now is just show you where it comes from. This is not something that you are required to generate yourself. However, it does help to kind of like look at the patterns and think about this for other types of problems. All right, so we want to find a Maclaurin series, and so we want to go ahead and start taking some derivatives. So f prime of x is going to be k times 1 plus x to the k minus 1. And then remember that k is a real number. And then if I actually, so this is Maclaurin, right? So we also need to find f prime of 0, which is just going to be k. And f of 0, by the way, is 1. Okay. So f double prime of x, we're going to bring that k minus 1 down, and then times 1 plus x to the k minus 2. So when I plug in 0 to that, I just, yes, okay, I get the k times k minus 1. Triple prime, I'm bringing down the k minus 2 now. And then I'm left with 1 plus k to the k minus 3 and f triple prime of 0, just as the k expressions. And let's go to the fourth. So we have k times k minus 1 times k minus 2, and then times 1 plus x to the k minus 4. And then when I plug in 0, I get just the k expressions again. Oops, and here I forgot my k minus 3, so I'm just going to move that over. There, now k minus 3 times that. So now when I plug in 0, I get the right expression, k times k minus 1 times k minus 2 times k minus 3. And so, of course, the big question is, what is f of n, or sorry, the nth derivative of x? And so here we have to look for the patterns, right? So clearly we're going to start with k and go to k minus 2, k minus 3, and so on. But the question is, how far are we going to go? Because n and k are different numbers. So we need to come up with an expression to represent when to stop writing those sets of parentheses. And then we'll come up with that expression, and then we're going to take that and multiply it by 1 plus x. And then we need some kind of an expression here relating k and n. So maybe that's probably the easier one to find. So looking at the patterns, all right, so we have the first derivative. And if we're just looking at the exponent, we have minus 1. We have the second derivative. Looking at the exponent, we have k minus 2. The third derivative, looking at the exponent, we have k minus 3. The fourth derivative, looking at the exponent, we have k minus 4. So it seems like it's always k minus whatever the n value is. So this can be k minus n. Now we want to figure out what goes inside this parentheses. So that's a little bit trickier. So again, here, let me maybe try this. All right, so on the first derivative, we just go to k. So k minus 0 would probably be a good way of thinking about it. On the second derivative, we go to k minus 1. On the third derivative, we go to k minus 2. And on the fourth, we go to k minus 3. So it seems like we're always going to the number that's right before the n value. So if n is 4, then n minus 1 is going to be 3. So it seems like we go from k minus 1 all the way down to k minus n minus 1. So now when we plug in 0, which I'll just do under here, so f, the nth derivative of 0, that 1 plus x term is going to cancel, and it's just going to be the k expressions. And I'm going to go ahead and distribute in that negative sign so I can remove one of the sets of parentheses. So I end up with k times k minus 1 times k minus 2, and so on and so forth, all the way down to k minus n plus 1. Now we want to put it into the Taylor series format. And so remember, that's going to be the series from n equals 0 to infinity of the nth derivative of a over n factorial times x minus a to the n. And so remember here our a is 0 because it's a Maclaurin series. So that's why we plugged in 0. We have our our nth derivative of 0 here. So now all we have to do is plug it into that expression. So we get the sum from 0 to infinity. So we want the nth derivative, so that's all of this stuff. So k times k minus 1 times k minus 2 all the way down to k minus n plus 1. And all of that is over n factorial. And then times x minus 0 to the n. And so this is our expression, or our series, that represents the binomial 1 plus x to the power of k. So what's interesting about this, and this is why it's called the binomial series, is that, I don't know if that's going to be dark enough, we'll try. But this stuff right here, I don't know if you guys can see that very well. Let's try and slightly darker one. There we go. So this one right here, that if we plug in, if we choose a k and then we plug in minus 1 and minus 2 and all of that stuff, and then divide it by n factorial, we're going to get the terms, we're going to get the coefficients in these rows of the Pascal's triangle. So whenever I think of binomial theorem, I think of Pascal's triangle. That's why I kind of wanted to show you that. There's another way that you'll actually see it written. Sometimes you'll see it written like this: n choose k, x to the n over n factorial. And that n choose k comes from the idea of the binomial concept, and that all of these terms are n choose r, basically, or n choose k. So what you need to worry about, so you need to just kind of know what this formula is. You need to have this down fairly well. But you do not need to be able to use it, you do not need to be able to generate yourself. You do need to be able to use it for problems like example 2. So let's do example 2. So in this example, f of x is equal to 1 plus x to the power of 1/2. So that's our k. K is 1/2. And so we want to use this formula. So this should be equal to the sum from 0 to infinity of, well, actually, you know what? Before we do that, let's, instead of writing out like that, because we have to look for patterns again, so that's going to be a little hard. So let's just kind of like write out the terms. All right, so 1 plus x to the 1/2. So the 0, when I plug in 0, is going to give me a 1. When I plug in 1, I get 1/2, because that's my k, times x over 1 factorial. When I plug in a 2, I get 1/2, because that's my k, and then 1/2 minus 1 times x squared over 2 factorial. And then from there, when I plug in a 3, I get 1/2 times 1/2 minus 1 times 1/2 minus 2, and then x cubed over 3 factorial. And then we'll do one more, so plus 1/2 times 1/2 minus 1 times 1/2 minus 2, and then times 1/2 minus 3, x to the 4th over 4 factorial, and so on. But that's enough to kind of see a pattern. All right, so I'm going to simplify that. So that gives me 1 plus 1/2 x plus, that's going to give me 1/2 times a negative 1/2 x squared over 2 factorial. And then the next term gives me 1/2 times a negative 1/2 times a negative 3/2 times x cubed over 3 factorial. Then on the last term, I have 1/2 times a negative 1/2 times a negative 3/2, then times a negative 5/2, x to the 4th over 4 factorial, and plus dot, dot, dot. Okay, one more simplification. Now notice what terms I'm kind of collecting and how I'm putting these pieces together to pay attention to the patterns that can arise. So the first two terms are pretty obvious. All right, now the next term is a negative, so minus. And then I have 1/2 times 1/2. So that's x squared over the 1/2. 1/2 is going to give me 2 squared. And then I have times 2 factorial. In the next term, I have a negative times a negative, so that's going to be a plus. And then notice I have 3, and then I have an x cubed in the numerator, and then I have 1, 2, 3 2's in the denominator, so 2 to the 3rd times 3 factorial. The next one gives me a minus. This time I have 3 times 5 times x to the 4th all over, and then notice I have 4 2's now, so 2 to the 4th times 4 factorial. So now if we look at this, there is a pattern starting to emerge. It doesn't actually start to emerge until we get to the third term right here. You notice that? Or n equals 2 term, n equals second term, let's say. And before that, it doesn't seem to kind of like follow the same idea. So what we can do is we can write our summation omitting the first two terms. And then from there, we're going to get plus the sum from n equals, and now since we omitted the first two terms, or skipped the first two terms from our summation, we're going to start at 2. So we're going from 2 to infinity. Okay, so now we have negative, positive, so we definitely have a negative 1 to the end. And the first term that we want to be n, so when we plug in 2, the first term we want to be negative. So when we plug in 2, that should be a negative. So I need this to be n plus 1, so that when I plug in 2, I get a 3, and then I have a negative 1 to the 3rd. Now, the coefficients are of the x terms are a little confusing. We'll talk about that in a minute. Let's talk about the x's. We do have x squared, x cubed, x to the 4th, so we've got x to the n. And then in our denominator, it looks like we have 2 squared, and then 2 cubed, and 2 to the 4th. So 2 to the n times n factorial. Now we still have to deal with those coefficients, which are a little bit challenging. You can think of this as 1 times x squared and 1 times 3 times x cubed and 1 times 3 times 5 times x to the 4. So it seems like what happens is that we're getting all of the odd numbers. It's not really a factorial because it's not going, 5, 4, 3, 2, 1. So we can't use factorial notation. So we have to come up with another way of also representing that expression or that set of numbers in a similar way that we kind of did above when we were looking at the k's, although it's a little easier. So the easiest way is just to write, okay, I go 1 times 3 times 5, and then I'm going to keep going until I get to something. And so you want to figure out what that something is. So remember, this is a number that we're going to stop at when we plug in n. So I want to be able to plug in n. When n is 2, I should be able to plug in n and get 1. And when n is 3, I should be able to plug in n and get 3. And when n is 4, I should be able to plug in n and get 5. And so clearly we have a bunch of odd numbers. And so remember that the expressions that can represent odd numbers are things like 2n plus 1, 2n minus 1. So those are the two most common ones. So let's see what happens. If I plug in 2 to this one, I get 2n plus 1, which is 5. And I definitely don't want 5, so that's going to be too big of a number. So let's try the one with the minus. So when I plug in 2 there, I get 4 minus 1, which is 3, which is still too big, so I need to go lower. So I'm going to subtract off. If I subtract 2, it'll become an even number, so I'm going to subtract off 3 instead and see what happens. So now when I plug in 2, I get 4 minus 3 is 1. Okay, that works. When I plug in 3, I get 6 minus 3, which is 3. That works. When I plug in 4, I get 8 minus 3, which is 5. That works. So that one works. So that's the best expression to use for that. And so there you go. I know that wasn't necessarily easy. This one does take a little bit of time to kind of wrap our heads around. Taylor polynomials are some of the hardest because of having to find these kinds of patterns and having to come up with ways of representing them. So get lots of practice in when you can, after you take a nice long break over the midwinter break, of course. All right. I hope this helped.